Once the TCAN has completed the test, the output is an Excel sheet that should look something like this. The time column records the exact time at which the absorbance was measured. Each column corresponds to a well, and the values are the optical density, aka OD, of the absorbance at each cycle. To analyze this data, we need to first access and utilize a custom command, which I will walk you through. First, you will go to File and scroll down to Options and select Customize Ribbon. Second, you will scroll down to the right column tab, click Developer, and then click OK. Once you return to the Excel sheet, you will see a new tab at the top called Developer. Click the Developer tab, and then select Visual Basic on the far left of the ribbon. This will bring up a large window. Next, you will want to click File, and then click Import File. Then, you will want to find your Visual Basic code, and click Open. The Visual Basic code should look similar to this. Feel free to copy this code. This code is essentially taking the total reaction time and subtracting it by the first data point. This data point is when the injection occurs, which is an outlier in this reaction. You can then simply click out and go back to your data. This is a lot of data, and to better understand and analyze this data, I've gone through and color-coded and inserted a plate map. Each column represents one of the 96 wells. The yellow area is the row B on the plate, which is just tris buffer. The blue columns are the control wells with the tris buffer, and the green wells are the enzyme dilutions. The find time command is taking our column of data, our column of time, and a constant of 0.2 to give us the calculation of the time difference between the completion of the injection of CO2 water and when the OD first falls below 0.2. To use this command, you will take a new row and then use the find time command on each column. You should get a row of values similar to what I have here. Once you have obtained these values, copy the whole row of them and go to a new sheet. On this new sheet, paste all of your values at the top row of the sheet. As you can see here, I've organized these values into a table. Now, we must find the raw unit activity, which is the enzyme activity for the whole solution. In order to find this, we will use this equation here. This equation is 1 over the dilution minus 1 over the control, all multiplied by a constant of 1000. Once you have generated all of the values in the table, you will want to make a new row, where you will take the average of the dilution values of each column. Next up, we have to calculate the milligrams of enzymes in our dilution. First, make a table with a column listing the milliliters of enzyme solution in each well, which is a constant amount of 20 microliters, which is 0.02 milliliters. The second column, listing the dilution factors, are all listed here. Then, you want to add a third column to generate the amount of enzymes. To find this, take your stock concentration. We used a concentration of 3.5, and then multiply it by the milliliters of solution over the dilution factor. Then, repeat this for all of the other dilution factors. Now that we have these values, the next step is to plot these points on a graph. For the x-axis values, you will use the milligrams of enzymes we just calculated. And for the y-axis, you will use the raw unit activity from the averages of the other table. As you can see here, I have multiple different charts. This first graph is all of the data points that we have, and it should be giving us a linear curve. So, to reduce error, we will remove any outliers that we have. The other graphs that we have here are simply the same data points, excluding outliers. As you can see, removing these outliers makes our graph far more linear. Based on our data, the more enzymes that you have in solution, the faster the reaction will be. These graphs help us understand and analyze the range of ability of these enzymes. This here is our final graph, where we have a slope of only 4 of our 6 data points. We can take the slope value here, which is a large number, so to make it more readable, we will put it in terms of kilo units. In this case, we have a specific unit activity of 1,300 kilo units. The specific unit activity is essential to measuring the catalytic ability of an enzyme. Your specific unit activity may vary due to various factors. For example, enzyme batches are different and can have different strengths and effectiveness. For our specific experiment, though, we found this to be our value. Alright, so you've now processed and analyzed your data. Check the description for more information, including the Visual Basic code.